Yeah, good afternoon, everyone. Thank you for the organization of this fantastic conference. It's really a pleasure to be here. I hope I will not repeat a few things that Rajesh already pointed out this morning. Hi, Rajesh. Unfortunately, I did share a PhD defense and couldn't attend your talk. I'm very sorry. So I'm going to talk about brain-artificial intelligence interfaces. And this is a little bit different from the brain-computer interfaces that some of you may be used to. So can we have the first slide, please? Or the second slide. So the next one, please. Thank you. So a BCI is defined as a communication system in which messages or commands that an individual sends to the external world do not pass through the brain's normal output pathways. And since the very humble beginnings several decades ago by now, where really simple motor commands have been decoded, we've really come a very, very long way. And I've brought one video for you that has recently been published by colleagues from Stanford University. Frank Willett was the principal investigator that really shows what is feasible today. And that is a BCI for speech decoding. So can we see the first video, please? So this is a patient with ALS, amyotrophic lateral sclerosis. She cannot speak anymore due to this disease. And she has these two implants on her head. And these implants, they go to electrodes that are implanted in her premotor cortex. And they measure activity from those muscles that control our vocal tract. And there's a machine learning approach behind that that tries to decode the phonemes that she internally attempts to speak, and then tries to decode from that which phonemes she has spoken, uses a language model, and tries to reconstruct the sentences. And this works amazingly well. So there are two different tasks that she can do on a very small vocabulary with a few dozen words, where she has a really low error rate and can lead simple conversations. And there's also one task where she has a very large vocabulary for more complex communication, but there the error rate is not really yet on the level where you could use this for everyday communication. Still, it is utterly amazing that nowadays, these patients who have lost the ability to speak can have implants in their head and lead conversations. Fantastic. At the same time, I wouldn't be showing this video if I didn't have something to criticize about this, because there are a few shortcomings. The first one is it is not entirely clear how this will scale up, whether for very large vocabularies that enable natural conversations, the error rates will be low enough, whether we have enough electrodes for that and so on in the brain. And the other one is that the group of patients who can benefit from this technology here is reasonably small, because this technology requires that your mental inner speech is still intact. The decoding is done from areas of the brain that control your vocal tract muscles. And there are patients like this, for instance, ALS patients with this bulbar form of ALS. However, the most common deficit, speech deficit, is after a post-stroke aphasia. And these patients with post-stroke aphasia, they typically have no intact mental speech anymore. So there we do not have the case for typical BCI that you have a healthy mind in a disabled body, but you actually have a disabled mind in a healthy body. And these systems wouldn't be able, or they couldn't be used by these patients who don't have any inner speech anymore. So I personally believe that in order to enlarge the group of patients for which such systems can be used, we need to take a radically different approach and not use machine learning and AI to bridge this gap from a healthy mind to the outside world, but rather, thank you for the next slide, that's the one, but rather use an AI that collaborates with a disabled person to together synergistically solve a problem. So what I'm going to show you is a first prototype that we built here in Vienna for a conversational brain-artificial intelligence interface, where a person here, the environment, wants to communicate with a disabled user. And of course, the user hears what the person says and communicates, but the AI agent also hears it. Now the AI agent and the user have to communicate in some way via brain-computer interface, such that the AI agent receives the information that it needs to speak for the user. And now you might say, maybe that's a bit strange that an AI speaks for somebody else, but thinking about it, the sentences, the words that I say here right now, I have no idea how I make them up. Somehow my brain generates these words, and most of the time I I'm quite okay with what I'm saying. Sometimes I say, oh, I wish I had said that differently. And I fear the future is going to be similarly for these patients. We will have AIs that will talk for these people and learn how to speak for these people and how not to speak for them. So the next video, please. I'm going to show you first prototype that we just recorded, a video that we recorded a few weeks ago. So this here is one of our PhD students, Anja Meunier, who was, is in charge of this project. And she acts as if she is a hairdressing salon. And this lady here, wearing this EEG cap, needs to call this hairdressing salon and make an appointment. So the scenario that we gave here is make an appointment in this hairdressing salon for Anna at Wednesday, 4 p.m. I think it was. Do we also have sound for this one?
Bye.
Yeah. Okay, the way that this works is as follows. Anja asks a question. This question is transcribed to text. What day would you like to come by? And then an AI in the background comes up with potential answers. And the AI understood here, okay, the question is what day would you like to come by? It's days of the week. So it comes up with the days of the week.
Okay,
and now the subject here simply looks at the keyword that she wants to select. And then there's this flashing going on. And these flashing patterns, they are different for every keyword. So our brain-computer interface can read out at which keyword the subject looks or focuses their attention on. And once that is correctly selected, the AI comes up with a suitable answer and then speaks out the answer.
The 4 p.m. slot works best for me.
Yeah.
Okay. Is the appointment for cutting, coloring, or styling?
Here you will see a small mistake. Yeah, it doesn't always fully succeed. So Anja said, is the appointment for cutting, styling, or coloring?
Styling, all of the above.
So, styling?
So the important thing is here, this AI running in the background has never seen the scenario before. Yeah, so it's not trained on the scenario. You can potentially speak with the system about any topic, and the AI will try to come up with keywords that express suitable answers, which you can then select without being able to speak. So here the subject selected the previous slot and will select styling again, I think.
I am sorry, I misspoke earlier.
Okay, is it for cutting, for coloring, or for styling?
I was calling about styling.
Okay, perfect. And what's your name?
So there's now a database in the background. What's your name? The AI understands that it now needs to provide context information. The AI has been told that this lady is called Anna, so it can fill in that information. Or display it and then have it selected.
Anna.
Okay, Anna. See you then.
Okay, so this is all still a bit cumbersome, right? It's a bit slow. The selection is based on these keywords with these cumbersome EEG caps. I think all of that will have to improve. But I believe the future is in teaching AIs how to take over tasks for disabled people that they cannot do anymore by themselves, rather than assuming that there is a fully healthy mind locked into this disabled body. With that, I would like to conclude. Looking forward to the discussion.